Now, what if we are drawing Lewis structures and trying to use those Lewis structures to create VSEPR models of molecules, and we end up with a Lewis structure that has a lone pair or a couple lone pairs on the central atom? Now, I'm going to tell you that lone pairs behave just like bonds. In fact, they basically are exactly the same quantity of electrons as a bond. They just don't have another atom attached to the other side. So they're going to do just as much, in fact, even a little tiny bit more repulsion than a bond would. So keep that in mind, that we are going to be viewing lone pairs as almost equivalent in repulsion as bonds. In this video, we will focus on molecules that have 3, 4, 5, and 6 regions of electron density surrounding the central atom and contain lone pairs on that central atom. So this is what happens. Let's try to draw the molecule O3. Draw the Lewis structure, and actually this one contains a resonance structure. So draw one of the resonance structures for O3, which is ozone. Now, hopefully in your Lewis structure, it looks something like this, or at least one of the resonance structures of this molecule. You're going to notice that we have 3 regions of electron density. We have 2 bonds on that central atom, and we have a lone pair. So if we have 3 regions of electron density, we can kind of picture the molecule looking something like this. Now, this would be a region of electron density, this would be a region of electron density, and this would be a region of electron density. However, this, we'll say this is going to be our lone pair. So we are going to say, all right, it will behave just like a bond because it still is 2 electrons, but it's not going to be attached to anything. It's still going to provide repulsion away from these bonds, but it's not going to be attached to anything. So if we completely remove that, I mean, we know it exists, we know those electrons exist and they're repelling each other, but if we remove it because we're only looking at where the bonds are, we end up with a molecular geometry of what's called bent. And this is because we have 3 regions of electron density, the 2 bonds, and that lone pair that's not attached to anything because it's not a bond. We have the 2 bonds and the lone pair, but we're just looking at the molecular geometry when we get to this bent name. Okay, so the electron pair geometry for this would be trigonal planar because they all exist in a plane and there's 3 regions of electron density. But the molecular geometry is now bent. And you can kind of think of that lone pair as an invisible force pushing down on these 2 bonds here. And actually, lone pairs have just slightly more repulsion power than a bond. So we would normally predict these bond angles to be 120 degrees. In reality, it's just slightly less than that. So they're just squeezed together a little bit more than they would if this was a bond. So 120 degrees is a good approximation, but know in your mind it's just slightly less than that 120 degree angle there. Now let's take a look at molecules that have 4 regions of electron density and lone pairs on the central atom. Now I think the most common one is water. So I want you to draw the Lewis structure for water. Okay, hopefully you drew something like this. You have oxygen in the center with 2 lone pairs on it, and that oxygen also has 2 bonds. So if we had 4 regions of electron density and all 4 bonds, this is what our molecule would look like. This is actually our CH4, but it's the same idea with the 4 regions of electron density. So our electron pair geometry is tetrahedral. This represents all the regions of electron density there. But 2 of those bonds or regions of electron density are actually, they're not bonds, they are just regions of electron density. They're just lone pairs, and they exist there and there. And what they're doing is they are also causing repulsion with these two bonds down here. So what we end up with is these invisible lone pairs that we know in our mind are repelling these two bonds. And we have 4 regions of electron density. The electron pair geometry here would be tetrahedral. But because we have 1, 2 lone pairs on that central atom, we have a molecular geometry of bent. And this is how you can picture the water molecule looking. Actually, you'll see most water molecules represented like this because oxygen is usually represented as a red sphere when we have molecular modeling kits. So if this is what you see, this is probably more accurate. And a very common way to represent water. And the reason it's bent like that is because of those invisible lone pairs. Now you'd expect that this would be 109.5 degrees across here, but in reality it's slightly less than that because the 2 lone pairs are squeezing those bonds together. So it's slightly less than 109.5 degrees for the bond angle of water. And it's because of those lone pairs up there pushing down. Now let's get into molecules that have 5 regions of electron density. So any molecule with 5 regions of electron density, so either bonds or lone pairs, 5 regions of that is going to have an electron pair geometry of trigonal bipyramidal. So this is our molecule that has 5 regions of electron density. So what we're going to do is I want you to draw the Lewis structure for SF4. So sulfur tetrafluoride. Okay, hopefully your Lewis structure looks something like this. Now, if you look at the central atom, there are 5 regions of electron density. However, not all of these regions of electron density are bonds. In this molecule, we do have a lone pair. And you're going to notice that there's 1 lone pair on it. So we're going to take out this bond here. Now, when we start removing these bonds from larger molecules, you're going to notice that we remove bonds, and imagine that they're now switched to lone pairs, around the flat or the horizontal plane. If we're holding the molecule like this, we remove those and we keep the top and the bottom atoms intact. So only the ones on the plane are going to get removed, and they get removed so that the repulsion still exists and they get removed evenly. That comes into play in the next molecule that we'll look at. So this one, we remove this. Now it's not completely removed. We have to imagine, that lone pair is still there providing repulsion. But if we want to just look at the shape of it and get that molecular geometry, this is called sawhorse or seesaw. That's the shape of this molecule. And the reason it's positioned like that with these 2 down here is because there's that invisible region of electron density repelling downward. So these bond angles are going to be just slightly less than 120, and these are probably going to be just slightly less than 180 degrees. Maybe even just 180 degrees depending on the size of the atom. Now the last type of molecule we're going to look at is one that has 6 regions of electron density around the central atom. So I want you to draw XeF4. So hopefully this is what your Lewis structure for XeF4, what it looks like, and we'll just take a peek at where the regions of electron density will be. We have 4 bonds. Those are the XeF bonds. And then we have 2 lone pairs on the central atom. So 4 bonds plus 2 lone pairs give us 6 regions of electron density. So the electron pair geometry is octahedral, and the molecular geometry for this, because it has 2 lone pairs, is called square planar. And you're really going to see what that looks like once we remove these. So we're going to remove the opposite sides, the electron or the atoms on the opposite sides. We're going to keep the top and the bottom intact. Always keep the top and the bottom intact if you're holding it, and then remove them in a way so that you will always have the most repulsion taking place. So in this molecule, you're going to see it's square, but it exists in a plane. So square planar is the name of this molecular geometry. And the reason it exists like this and not tetrahedral, like CH4 would be, is because we have these invisible lone pairs providing repulsion. So that R in VSEPR, valence shell electron pair repulsion, that R is essential in all of this and in determining where those atoms are going to be in relation to the lone pairs on a molecule.